get back. I'm alright, Jack. Keep your hands off of my stack. Money, it's a hit. Don't get me back to good bullshit. I'm in the high-fidelity first-class traveling section. I think I need a lift jet.
Good morning, everyone. My name is 𝗧𝗦𝗦𝗬𝗓. I'm with Lakeside Process Controls, the process optimization specialist. With me here, I have Devin Marshman from Spark Controls. Um, Devin, why don't you
Hey,
tell
Sylvain.
us a little bit about who you are and what you do at Spark Controls?
Sure, thanks, Sylvain. So my name is Devin Marshman with Spartan Controls for 15 years. I'm a chemical engineer by training with a master's degree in process control and optimization. And I've been working with Spartan for the last 15 years doing advanced process control in the processing industries.
Awesome, awesome. Thank you very much. I have I don't have my master's degree. I'm not that smart. I have 30 plus years experience in process optimization, control audits, loop tuning, instrumentation troubleshooting, and things like that. So, for those of you who are interested, the little black and white squares you see there, apparently that contains all my information. So you can go ahead and scan that. You'll be seeing that later on as well. Should you need to have additional questions later on. Some guidelines, first of all, so your microphones are off, so we will not be able to speak to each other. Um, you can ask questions. There'll be a Q&A sessions later on, but you feel free to type in your questions anytime you want. We will answer them at the end of this session. Uh, there is a 10-second time delay from the moment that we speak to the moment that you actually hear us, and that is because our platform gets a better buffering capability. So if you think that light travels at 300,000 kilometers a second, that means that technically we could be 3 million kilometers away from you. So we could be near the Lagrange point, near the James Webb Space Webb Telescope, if I can speak. And so I actually get some element 115 from Bob Lazaro, and I filled up our flying saucer, picked up Devin on the way up, and that's where we are. So we can see your questions. I'm pretty sure only we can see your questions, so we can actually. So there's no bad questions. I encourage you to actually ask questions. There's no such thing as a bad question as well. And like I said, feel free to reach out to us, to myself. Should we have any more questions afterwards, or you didn't get a chance, or you weren't comfortable, that's fine. Feel free to reach out to us later on, and we'll make sure that we answer your questions. And once again, there's that little QR code with all my information there. There is a handout. So if you actually go at the top, there's a section that says handout. You can download a PDF. Sorry to go back to here. You can download a PDF. There's a paper written by Devin and a colleague. If you do actually see if you do any kind of Google search on, we'll talk about this later on, IQC or integrated quadratic control and mining industry, Devin's name keeps popping up all the time. So so anyway, so this is one of the papers that he presented. Interesting reading. So you are free to download that. And this is a series of webinars that I actually have put through here. This is the first collaborating one, but I put through a whole bunch of series of webinars. These are all recorded. Should you wish to view them, just reach out to me. I can send out the link for you. And they are pre-recorded. They are free. So you're more than welcome to. Some of them have music to them as well. So for those of you who are local, on Thursday, this Thursday, so Tuesday, 2 days from now, we actually will be having in our offices in Mississauga, 3 million kilometers away from us, there will be an isolation actuation mining seminar, and you are welcome to attend. Again, it is free, and I actually will be there as well to do some demonstration as well. And it's a full day event, and we feed you very, very well. So again, if you are in the area, you are interested, you are more than welcome to attend. As are my other webinars, this is actually recorded. So if you want to go back and take a look at it, if you want to say, hey, this is so good, I'm too sad that my colleague missed it, you can tell them, hey, it's recorded, and we can send you the link, and then you can review it again. And you can actually even fast forward through all the boring stuff that I'm talking about right now. Bit of a safety moment. I know we kind of passed the equinox back in March 20th or 19th, 20th, I believe, and we all survived here in Southern Ontario. We survived the eclipse, thank God. But one of the things as well is to always following. They always tell you to change the batteries for your smoke detectors, but as well as your carbon monoxide detectors. So I know that in my house I have at least we have four carbon monoxide, so one in each floor, and including the basement, and one in the garage as well. And so it's important because I actually have my winter barbecue in the garage. So I do barbecue in the wintertime with the door open, obviously, but I do have a carbon monoxide detector there as well, just in case. So be very aware of that as well. A little bit about Lakeside. It says 325 employees. It's just probably kind of dated. We actually have well over 400 employees now. We have offices in obviously in Mississauga, Sarnia, Sudbury, Port Elgin, Dundas, Ontario, Thunder Bay, and Winnipeg. And the one in Dundas is kind of exciting. It's a newer facility. It's where we do a lot of our fabrications for skids, a lot of our valve repairs, instrument repairs are done there as well. So we're quite proud of that. It's a huge six 6 million square feet. It's a very big. I can't remember. It's in the millions or thousands. I can't remember. And we are part of the Emerson Impact Partner, as is Spartan as well. So our territory at Lakeside is most of Ontario, just this side of the Kingston side to the Manitoba Saskatchewan border and parts of Nunavut. And Spartan Controls takes care of the western side from Saskatchewan to BC and most of the Northwest Territories and so forth. So we do work together a fair bit on some of these endeavors. So what are we going to talk about today? Explain a little bit the relationship. I kind of already hinted that we're both Emerson Impact Partners, and then we're going to talk about obviously what is advanced process control, and then the most important why. We're going to deal also with some of the application that Spartan has developed, Spartan Pro Solutions. And specifically going to be the grinding, flotation, and thickener. Now, we're going to hint at this later on. There are many other applications, but we kind of limited to the what I call the 80-20 rule, the bread and butter, where you probably get the most out of your money as well. And then we talk about how specifics, and then how where do I begin in terms of okay, I'm interested, what are the opportunities and so forth. We'll talk about how the timeline to actually implement these as well, and obviously the most important part is the and it's always that key word nowadays, sustainability. How do we maintain the system to make sure that it does not degrade over time? Yeah, sustainability, I know. So as I mentioned, Lakeside and Spark Controls we're both Emerson Impact Partners. We are the exclusive reps for Emerson process automation products within our territories. But we also have an agreement together, so we rely on each other. Sometimes we have expertise that Spartan does not have, and then Spartan has obviously expertise that Lakeside doesn't have, and so we lean on each other to be able to bring more complete offerings to our customer base. And this is what we have right here. And for the Spartan Pro Solutions, again, obviously today we're going to talk about the mining application, but I think there are Spartan Pro Solutions for all these industries out there. from obviously in the oil sands, which we don't have here in our territory, but pulp and paper, the lime kiln application, power and utilities, and so forth. So this is just a small subset of the solutions that are available to the industry. Now, so Devin, so here we're going to talk about today. We're going to talk about hard rock application. So we're talking here AC/DC or maybe Pink Floyd, maybe a hard rock application. So we got Spartan Pro SAG mill. So SAG mill, if I remember, semi-autogenous grinding,
Nailed
right?
it.
I
Yeah,
nailed
you
it.
got
All
it.
right, all right. It's autogenous. All right, and the ball mill. Uh, we got soft rock applications. And then more common application, we got flotation, thickener. And today we're going to talk about these three groups of application, I think. And and Devin, correct me if I'm wrong here, but I think these are probably the most common for mineral processing. I'm not talking, molybdenum or copper or gold or nickel, but these are the more common types for all mineral processing. Am I right in saying that?
It definitely in Western Canada.
Okay.
There are variations, lots of leaching and electrowinning circuits out there for sure,
Right. Right.
which we're not going to cover today, but we can be happy to talk about at a later date.
Awesome, awesome. And you can see here, there's a lot of other types of solutions as well. Should you have any questions about these, feel free to reach out to us, and we'll make sure that we can answer your questions and maybe provide you with a more personal type of presentation, should you want to. Now, this Spartan Controls has a tremendous amount of experience here. So you can see it's a bit of an eye chart. Um, But maybe Devin, I'll let you speak to this because obviously I'm not completely familiar here. I'll let you speak to this in terms of the benefits that has been achieved by advanced controls.
Yeah, you bet. So I won't talk about it line by line or anything, but really one of our mandates is to work with customers to set up advanced control applications that help their process and save them money, make them money, essentially. So we've been doing this in the mining industry for over a decade now. Most of these applications are kind of these big three that we're talking about today: the grinding circuit, flotation, and thickeners. But lots of other solutions in there as well. Now, the exact values that customers are saving aren't listed here. Some of that's proprietary. The biggest application I'll mention, or the biggest payback that we've achieved for a customer, is upwards of $36 million a year. Now, that's
Wow.
gonna yeah, and it's of course it's gonna vary based on your mine size, based on your mineralogy, um, based on your current operating conditions and where you set the bar. Uh, but generally, there's some pretty high paybacks available for
Wow.
these applications.
And what's a sort of kind of, I mean, obviously it ranges here, but payback period from the moment of implementation, commissioning, and then operation, what kind of payback are we talking about?
We're definitely talking months.
Months. Okay.
Months. Yeah,
So that's not years or like
and
that. So
and weeks in the case of, or days in the case of 36 million.
no
Definitely,
kidding.
it's
Wow.
pretty quick.
Wow.
Yeah.
That is amazing. That's amazing. So why are we talking about this? Let's take a look at mineral prices. Some of you may want to look at this, some of you may not. But let's take a look here. These slides are tad dated here, but gold seems to be, this is over a period of 1 year, and you can see gold kind of always seems to maintain its value, but then depends on a whole bunch of other geopolitical situations that are happening right now. You look at here, nickel, kind of a bit of a depressing slide where it seems obviously prices have dropped. I'm not exactly sure what the current prices are now. Copper kind of hovers around. I can't remember now. You might be recovering a little bit. Palladium, for a while there, palladium during the pandemic, I think there was palladium was more expensive than gold. It seems to come back to reality at this point. Uh, so why am I showing you these depressing slides? Well, basically, advanced controls is there to. We'll talk about this a little bit later on to be able to maximize your throughput, but also maximize your extraction of your process. So you get the best of both worlds to be able to weather these kind of fluctuations, which are inevitable for mineral prices as well. Another reason why, at least in Lakeside's territory, we got this is kind of what we have right now: over 16 active gold mines, 16, and one in Manitoba, and there are 13 more potentially active and advanced exploration stage within a territory, and you can see the rest here. So the mining is huge, and we're not even talking about the Ring of Fire here, which is the chromite deposits that are up north, which are still happening. I'm not exactly sure where we are, but we're not even talking about that. So mining is a huge part of our customer base, huge part of Ontario's economy. So something that we need to make sure that we need to capture and make sure that we are there to be able to support and actually be as efficient as we can. Another reason why, obviously, as I talked about that, we talk about increased throughput. So times are good. Let's get the product out the door. Increase yield. Times are not so good, but let's make sure that we get as most as we can out of that. Energy cost, our favorite energy cost. So last April 1st, we had our, which unfortunately was not a joke, we had our carbon tax increase. Today, April 16th, we got the federal budget. It's all going to be all sorts of goodies here. So obviously, to be able to reduce our carbon footprint is very important. The carbon tax, greenhouse gas emissions. And one thing that, Devin, I want to talk to you about, the very last one says government incentives. So you've had some experience with government incentives. Can you say a few words about that?
Yeah. I'll we could have a whole webinar on that, but to keep it brief, there's lots of incentives out there around reducing energy consumption, specifically greenhouse gas consumption, both from provincial governments and from the federal government. So across Canada, which is applicable to, I think, everyone here, there is funding through NRCan, and for large projects that reduce greenhouse gas emissions, they can fund, depending on the time and of the application, 25 to 50% of projects.
25 to 50%. Wow,
mm-hmm.
that's huge. That's huge. So like I said, so not only do we, you get the benefits, but also you can get subsidies and help from the government. May as well get all the help we can get from our government.
Yeah, get that carbon tax back.
Absolutely. That's another. I mean, we're not going to get on our soapboxes here, but. All right, so let's talk about, before we talk about advanced controls, let's talk about what simple control is all about. So we talk about a single input, single output. And we're all aware of, you have our controllers out there. Here, let's say we got our flow controller. And that the output of that controller will talk to a control valve of some sort. That will affect the process. Could be a grinding, a cyclone, could be a flotation cell, could be all sorts of things. And eventually we measure what we need to measure, and that's what we call the single input, single output. So just bear with me for a second here. Just had to clear my throat there for a second. All right. Whereas advanced control deals with multiple inputs. So what I'm showing you, so you can see here, it says MPC Pro. I just want to clarify. I know in Delta V speak, we got MPC, we got MPC Pro and MPC Plus. Depending on what your requirements are, we're probably going to end up, and Devin, again, we're probably going to end up with MPC Plus. I think that's sort of the more advanced, the more flexible, the more applicable. No, am I right in saying that?
Yeah, that's fair. And though, technology will depend on the application, which we'll talk in a bit here.
Okay. So we got multiple inputs. So you can actually bring in several measurements in, and then that block can actually talk to multiple outputs, to multiple valves. That will then obviously affect your process, and everything comes back. So the key here is, first of all, nomenclature. So before we talked about process variables for a single output, single output, single input, single output controls. Here we're talking about control variables. So what are we trying to control? What are we measuring? And the MPC Pro then talks to the outputs, and those are known as manipulated variables. What makes the MPC special is that it can take into account the different interactions. So if I'm moving one valve, it may affect a couple of process measurement control variables. And so what it does is that it can take into account that interaction. So whatever control action it takes, it can take the equal and opposite reaction to minimize the interaction with other variables. So that's one of the things it can do. It can take into account disturbances. So for those of you not, disturbances, basically other measurable disturbances, like basically you think of it as feed forward. So something happens, we understand that when this other thing happens, it affects us. Therefore, if we measure that, we can then compensate for that disturbance coming through. Constraints, so therefore we don't want to go above or below certain conditions, whatever they are. It can also take into account long process dead time. So for a PID controller, I always say that dead time or time delay is the enemy of a PID controller. This is a good dead time compensator that takes into account the fact that there is a lot of dead time to not to overcorrect. It'll actually build some weighting in there. It's essentially we're building a model inside the controller which takes that into account in order to compensate for any kind of time delays. So a little bit more, and then obviously you get to understand, get to talk to the really smart guy here, Devin. But so how do we do this? Essentially, for if you have a Delta V system, and I know you don't all have a Delta V system, but the MPC application runs native within the Delta V environment. So it actually executes natively inside. It's a pretty open box. I've actually been playing around with it, managed to get it everything going within a matter of a day and a half. So without having any kind of training. So it's pretty, very flexible, very open, very easy to use. Now, obviously, well, what if I don't have a Delta V? Well, we can still actually implement this application within a PK controller or whatever technology and communicate via OPC UA. I don't know what the UA, what does UA stand for, Devin? Didn't you know?
Oh, no, I'm not sure.
Ultimate access. We'll just make
Sure.
something up.
Yeah.
So OPC,
right.
UA, LA, SPCA, who knows? But it basically through OPC, be able to communicate with your controls to be a PLC, be another DCS and things like that, and communicate back and forth. So it's not the end of the world if you say, well, if I don't have a Delta V system, it's not the end of the world. Now, I know you guys, Spartan, you guys have done this a fair bit of time, not just in the mining industry, but throughout many industries. Do you have an
Yeah.
idea how many systems you have done this with?
We've done it on uh, roughly 10 sites, but
Okay.
within those 10 sites, we've done about 30 applications
Okay,
that
30 out
are
at
that are
10 sites.
running, yeah, in Delta V on top of other systems, and those other
Got it.
systems range from Foxborough, ABB, Honeywell, you name it,
Got it. Awesome. Awesome.
Rockwell. Yeah,
Now, they're not all mining industry, but I mean, the thing is that the concept is there, is that it's very applicable and very feasible.
yeah, exactly. Layering on Delta V for the advanced control functionality.
Okay. One last thing, but like I said before, we get into the really interesting stuff here is, and I'll get on my soapbox here a little bit when I talk about how loop tuning. I talk about loop tuning and my courses that I teach. The first thing I say is that loop tuning is the last thing you do, which is kind of ironic, because the first thing we need to have is a proper process design. Make sure the pump sizes, the tank sizes, line sizes, grinder, flotation, all that. We have to make sure that it's properly designed for your process. If we don't have a properly designed process, we're not going to be able to control. Next thing on top of that is control strategy. How is it programmed within your control system? Do we have feed forward control or not? Do we have MPC control or not? Or have we thought about doing MPC control? After that is instrumentation. So on one side of the equation, we got to have the right instrument properly specified, installed, and maintained. I'll repeat it: specified, installed, and maintained. If we don't have that, we're not going to be able to control properly. And the other side of the equation, you got to have the valves that are precise, dynamic, and properly sized. If we don't do that, we're not going to be able to control. Now, typically here, I would say after that, loop tuning becomes effective, but then we could carry it one step further, because then only then will advanced control be effective. So our approach will always be from a bottom up approach. We're not going to tell you, hey, we're going to slap on some advanced controls on your system and everything's going to be better. No, we're going to have to do our due diligence and make sure that we actually do our due diligence, make sure that all that is done properly. And then we'll say, okay, so now let's talk about doing some advanced controls. I don't know, Devin, you have anything to add to that?
Yeah, well, first of all, you're exactly right. Like a well-designed, perfect advanced control strategy is not going to work if your instrumentation is spitting out garbage information to it. So that foundation absolutely has to be in place. I'll also just mention there is one level higher. That's that real-time optimization at the top of the pyramid. That type of strategy typically looks at an entire site or even an entire enterprise, depending on the application. And tries to coordinate areas within that mill. Now, again, just like advanced control, you've got to build up to it. So, and until you have that regulatory control foundation well established and advanced control coordinating the individual unit operations, it's a little premature to think about real-time optimization. But it's a decent end goal to have in mind, and there are the benefits in going after that for sure.
Awesome. Good stuff. So there we go. All right. So here, like we talked about here, we're going to deal with obviously the grinding circuit here, and I'll just talk a little bit through this here. So maximize throughput. Obviously, all these objectives is we're going to deal with a flotation, as well as we're going to deal with the thickeners as well. And so maybe what we could do is just go right through here, and finally I'll be quiet here and I'll let you take this over, Devin.
Yeah, and I'll just add, that process flow diagram is a sort of a typical one for copper sulfate processing. I realize that all of the processes out there are probably going to vary from this, some to small degrees, some to large degrees, but we're just using this as kind of the standard benchmark to walk through.
Awesome.
So starting with the grinding circuit, this is right at the front end of the mill and is really responsible for getting the particle size ground down to a level where you can actually process it or separate it within flotation typically. Now, a lot of the time there are, again, lots of different configurations out here, but a really common one for hard rock metal mining is to have a SAG mill followed by a ball mill grinding circuit. So SAG gets the particles down to a relatively fine size, and then the ball mill takes them a little bit further. And yeah, it really about efficiently grinding down those particles to an efficient size. So when we're talking about advanced control, we're typically trying to maximize throughput and minimize power use while maintaining that grind size. So looking at the SAG mill, it's one of these multivariable applications, like somebody was talking about earlier. So there's not just one handle that you can manipulate to try to control grind size or loading in the SAG mill or power draw in the SAG mill. Really, if we're going to operate this, you're controlling feed rate, you're controlling speed of the SAG mill, assuming there's a VFD on it, which there usually are in large operations. You're controlling the recycle rate and water addition in there. So any operator that's looking at this has to sort of coordinate all of these things and manage them together to maintain a stable density within the SAG mill, a load in the SAG mill, grinding efficiency, and setting up advanced control. We have to consider all these things as well. One key point here is like that autogenous term in SAG mill, like Sylvain was referring to, really comes from the idea that you're smashing rocks against other rocks in here. So basically what you want to do is load the mill up and rotate it so that the rocks get up as high as possible in the SAG mill and then come crashing down into other rocks. Now there's metal balls in there as well that do this, which is the semi part in 𝗦𝗧𝗔𝗬𝗓. But basically, if you underload the mill or spin it too fast, you're going to end up taking the rocks up higher and hitting the liner, which is really detrimental and can reduce the wear of the liner, significantly reduces grinding efficiency and takes more power. If you overload the mill and fill it too full, basically it gets too full, and then slamming rocks down into other rocks isn't very effective. You don't grind it enough. It's a bit of a self-fulfilling problem, because then material isn't getting ground and exiting the SAG mill, and you just build it up and run into these overload conditions. So in addition to coordinating control, you have to manage these kind of abnormal situations. One really key piece of technology here, we can work with loading in it, usually measured by bearing pressure. But if you have a mill slicer or an acoustic array that really looks for where that toe is, so where the rocks are impacting other rocks, and controlling that location, that really helps us do an effective job. So again, that foundation's got to be in place.
Awesome. And I guess these are examples here of just real life examples of the application of grinding controls here, right?
Yeah, this is before versus after. So a nice snapshot looking over several weeks before versus after. So the top is manual operation, where operators had that high limit where it would alarm. And basically we're reaching maximum SAG mill loading. Now, really the alarm was below what the real limit was, but with changing feed conditions, changing density, changing particle sizes, it would go up and down, and it would kind of be all over the place. Whereas when we were able to put in advanced control, we're able to tighten that variability and push it up towards the limit, and actually increase throughput by 2.5% here on a SAG limited process.
Nice.
Now, over the long term, they were actually able to take that limit and move it up because they felt more confident that the controls could maintain it below it safely, whereas they had lots of excursions previously. So long term, the benefit was more than 2.5% there.
This is
nice
awesome.
clean snapshot.
So your classic optimization of tightening up your your variability, and then shifting your target one way or the other way. I mean, this is your classic example there. Awesome.
Yeah, so that one's worth millions of dollars.
Yeah, I imagine. Let's talk about ball mills here.
Yeah, so ball mills are downstream. Usually get ignored because of SAG mills, but they definitely have to be considered within the same strategy. Really, depending on how hard you're running the SAG mill and how efficiently you're grinding in there, you can put a lot of load on the ball mill circuit. So really what we're looking at here is how much load is recirculating within the ball mill. And we want to run that as efficiently as possible and make sure the cyclones are doing a good job of separating. So control density and pressure based on the number of units open. But another key piece of this is that if the ball mill circuit is getting too overloaded and there's nothing we can do about it, we need to cut back on the SAG mill to prevent from having to stop everything and dig out the ball mill. So that's another key piece of maximizing throughput there.
Okay, so the two would be coordinated together then, right?
Absolutely.
Okay.
Yeah.
Okay.
Yeah.
That's awesome.
Yeah.
Let's talk about flotation here. So flotation, maybe you can describe a little bit what flotation is about and how we can help.
Yeah. So basically in flotation, you're basically getting the feed right from where we left off. So coming off the cyclone overflow from the ball mill circuit, typically. And of course, there's many flotation cells. I'm usually talking about roughers here, but there's cleaners, scavengers, regrind, tailings throughout the circuit. Either way, they're getting the feed, and they're applying a surfactant to that feed. And what that surfactant is designed to do is it'll be developed depending on the mineralogy, but it will bind to the desirable material, and it will make that desirable material hate water. It will make it hydrophobic. So it basically wants to get away from water as quickly as possible. So we put it into the flotation cell, and we pump in small bubbles of air down to the bottom. Those bubbles of air rise to the top, and then those hydrophobic particles that want to get away from the water, well, they see their opportunity and they bind to the air. And the air floats up to the top, and it basically carries over those desirable materials that have the surfactant applied through these concentrate launders. Whereas the undesirable material, which hasn't had surfactant applied, it's happy staying in the water, so it exits via the underflow.
Okay. Okay. So there's
Now,
one stream in and two streams out then. Well,
yeah,
actually, plus the air. Okay.
yeah. And I should note, like, these can be reversed, so you can actually add surfactant that binds to undesirable material and float the undesirable stuff. But typically, it's the desirable stuff that's being bound.
Got it. Got it. So it's funny with flotation. Actually, I was used in different industries. I know it's used in the oil sands as well to kind of float separate the oil
Hmm.
as well. It's used in pulp and paper for the opposite, for de-inking, where you're trying to get the ink particles out and you're floating. The bad stuff goes upstairs, and the good stuff is downstairs. Actually, so flotation is used differently in different industries. Kind of always
Yeah,
kind of interesting. So.
water, wastewater, it's in there too, for sure.
Yeah, exactly. Yeah, that's right. Yeah.
Yeah. And yeah, really here, so there's lots of ways to control flotation. Lots of inputs there. You can change the amount of flocculant you're adding or surfactant that you're adding, the amount of air that's going in, and the amount that you're opening and closing that underflow valve to push more through the bottom or over the top. But really what we're trying to do is pull as much product as we can over the top. Now, there is a trade-off there, though. So the more product you pull over the top and the harder you pull, the more air you put in, the more material you push upwards, the more of your product you're going to recover, but you're also going to start to recover some of that undesirable stuff too. And if you push it too far, then basically you're undoing the separation that a flotation cell should be doing. So there's a bit of a sweet spot there. We want to pull as hard as we can so that the final product grade is going to be on spec, but no harder, so that we're maximizing recovery. And this is really where the value is in flotation control.
Okay. So being able to actually, yeah, that pull rate then.
Yeah.
So the best thing is somebody could do is tell you whether rougher, blah blah blah. You could look at the way it looks. So you could look at the way looks the way it ought to look. Then you take a good long look and try to keep it that way. So which is interesting. So basically, this is kind of old school type, right? I mean, this is probably you got an operator, and I'm sure they are, and I'm sure. And listen, I'm not saying anyone's wrong here, but you can look at it, and if you got a lot of experience, you look at it and say, "Yeah, it looks good," or we need to add this, we need to add that," and that operator obviously knows what how to operate this. But then you get the next shift, and then different person, different personality, different levels of experience may not know or may operate it different or may not know as much as the other operator. So we're kind of looking here like a looky feel kind of deal. And what we're trying to do here with this is to have a consistent scientific operation. I kind of equate it to making either you're making chili or you're baking bread. And you're making chili, believe me, my chili, you taste it one day, it's going to be good, but it's never the same. But when I'm baking bread, believe me, I measure everything down to the gram level because obviously it's very sensitive. And it's obviously, I want to make sure I make a good loaf of bread every single day. So I have to measure, be scientific about it. So I kind of equate it to that. It's kind of maybe kind of a bit of a hokey thing, but so go ahead, Devin. Sorry, I got off on my tangent here.
No, it's a good analogy for sure. There are operators and metallurgists that can do this super, super well, but like you said, they're not standing out in front of the flotation cells 24 hours a day. So our philosophy, or coming into this, designing it about a decade ago, was there's a better way to do this. Now, flotation is an under-constrained system, and I want to talk about this for a little bit, just because it is kind of an important core concept in the way that we're going about the control. So really what we're trying to control here is the pull rate of concentrate over the top. So how much you're getting of that product stream into that overflow launder that exits. But there's lots of ways that you can control it or adjust it. You can increase the airflow. You can increase the level in the cell by closing off the underflow valve. You can add more frother, and in some cases, you can add more. You can dilute the feed stream coming in as well. So lots of ways that you can make the level go up or down, the pull rate go up or down, depending on whether you want more or less coming over the top. Now, typically an experienced operator, they'll move all of these things together. And the reason for that is that, you don't just want to pick one and only use that one thing to try to control. like if you're using frother, for example, adding a little bit more might get you a little bit more recovery because you're buying into more of the product, but you're eventually going to reach the point where you're saturated on the amount of frother that you can add, and it, just is essentially wasted, or it starts binding to undesirable material and floating that over the top. Likewise with air, if you're increasing the airflow rate a little bit, you start to make more bubbles and send more over the top. But if you send too much air, you essentially start to boil it. Or it looks like you're not actually increasing the temperature, but it looks like you're boiling it. And it gets so volatile that it's just pushing that undesirable clay and dirt and stone over the top, and you end up with an undesirable situation. So what you want to do is you want to move them all sort of together. Now, this is going to vary from process to process, and it's going to change based on the metallurgy at site, specific composition of what's coming in, what the inerts are, all that fun stuff.
So under constraint, then it's a little bit. Then you're saying that there's a combination. There's no one magical definite answer. Is that depending on the manipulation of 3 or 4 variables, and it could be in different combinations of these outputs that can actually achieve a specific pull rate, right?
Exactly. Yeah,
Okay.
and it's pretty different from a lot of control strategies that are constrained or over constrained systems.
Okay. You know what that reminds me of? I have I got my truck, and I don't have the fancy climate control. I just got the good old fashioned. And it's kind of like, in the wintertime, I'm sure some of you out there, I can adjust the fan speed, and I can adjust the temperature. And depending on, I can have a low fan speed, high temperature, or a high fan speed, lower temperature. There's multiple ways of achieving the proper temperature within the cabin, I guess. So, and I guess that's what we're talking about under constraint. You got 2 knobs to adjust, but various combinations can achieve the same result, I guess.
Absolutely. Yeah,
Okay.
you can.
Awesome. All right. I just want to. So, okay, go ahead, Devin. Let me go back here. So, go ahead and talk about this here.
Yeah, so this is a clearer picture of that under constraint setup. So
Okay.
again, we've got one thing we're trying to control, concentrate pull rate. We've got multiple ways to do it. So in this case, it's reagent addition, airflow rate, cell level. It could be water addition, airflow rate, cell level. But either way, we've got multiple ways to achieve the same solution. So really what we want to do is we want to move these things together to be able to control concentrate pull rate. And again, the way that we're going to do that varies depending on the metallurgy, depends on the specific equipment in the cell. But we know we want to move them all together in the same direction so that we get good, consistent, repeatable operation.
So I see there it says IQC. It doesn't say MPC. What's IQC?
So IQC is our solution to this under constraint problem, and it stands for integrating quadratic control. So it is essentially designed to look and feel like PID control, but for these under constrained systems where you have multiple outputs. So instead of having one gain, rate, and reset, you'll have multiple gain, rates, and resets. And basically it'll do PID control, but then it'll split the output between the 3 signals, depending on where they are within this kind of optimal operating envelope. So what we get operators and metallurgists to do is set high and low limits for where the process should be running under normal conditions. And again, this will vary site to site. It'll also vary week to week, depending on where the ore is being supplied from right now and what that feed mix looks like and what's going on upstream. Maybe there's a couple of cyclone units down, so you're getting coarser material than you're used to. So basically, operators and metallurgists will be able to go in and define these upper and lower limits. And then depending on where those variables, airflow rate level and water reagent addition, are within those limits, IQC will coordinate them and move them together so that they're the same distance from the upper and lower limits at any given time.
Okay. All right. Interesting. So it kind of finds its place based on the setting. Obviously, here there must be some sort of lab testing that has to be done by the metallurgist, as you say, probably on a daily or weekly basis to adjust these limits so that over a period of time as the grade of the ore changes. Correct?
For sure. Yeah. And the challenge is that a lot of that stuff is not measured in line. Definitely not at each flotation cell. So if it were, we could tie that back and close the loop around some of these upper and lower limits. But for now, what we found is, customers have had great success, basically just setting the boundaries for the process and then allowing IQC to control it through upsets, through changing feed conditions to provide consistent, stable operation.
Okay.
Now,
Go ahead.
yeah, so continuing on the cycle, I was talking about control of a single cell, but usually these cells occur in banks. So there'll be 6 cells in a rougher bank or 8 cells in a rougher bank. And really what you want to do is not just control individual cells, but control the net pull rate off of the bank. So here's kind of where the next step in IQC comes in, is we want to manage these cells all together. So really what we're trying to do is control the net pull rate off of the bank, and we'll do that with IQC again. There's multiple ways to achieve it. We could just pull it all from the first cell, we could pull it all from the last cell, but really what we want to do is we want to sort of evenly, consistently split how much we're pulling off of each cell to maintain stable operation. So each cell will have its own IQC controller, and then each bank will have sort of a supervisory controller that's in charge of coordinating them.
Wow. Okay.
Then, of course, there's one more on top of that. So you don't just have your roughers. Typically, you'll have your roughers, your scavengers, your cleaners, your tailings, flotation banks, and really what we want to do, and this is getting to that real-time optimization supervisory level. But we want to coordinate all of those together to make sure that we're pulling as hard as we can off of the right locations and controlling to that final product grade specification. So we want to kind of meet the customer requirements, or the selling requirements for the final product, but we want to get as much off as possible. So typically, if we want more product, we'll pull a little bit harder on the roughers rather than pulling a little bit harder on the tailings flotation, because that's not going to get you more bang for your buck.
Right. Right.
So there's a bit of an art in splitting that, and for that, of course, we're going to use IQC one more time, and it will actually coordinate. If you go to the next slide there, Sylvain, how much you're getting off of. Hey, click one more time there. It'll coordinate how much you're getting off of each individual bank. And again, we'll have the metallurgists and operators set limits for how much you want to pull off of each one. And then the IQC solution will manage disturbances coming from the grinding circuit, disturbances based on change in feed conditions, react to those and keep things nice and stable, while making sure that we're hitting but not really exceeding our product grade. And this is really where you get into the money piece, because that's full circle, right?
Yeah, exactly.
Yeah.
Awesome.
So really we want to make sure we're pulling as much as we can and hitting that final product grade. And this is sort of what that strategy looks like.
Got it. Okay. So there's a coordinated approach all the way across. That's impressive.
Yeah. So we've had a lot of success setting this all up across, multiple, across all the flotation banks on site to control final product grade.
Okay.
And then, of course, have a nice, easy to understand user interfaces with pretty substantial returns. And again, it's really tough to measure how much benefit you're getting off of flotation, because there's so much going on and you're not measuring concentrate typically off of each cell or off of each bank. So you only really measure final product grade and tailings grades. But in terms of quantified benefits, this customer was able to isolate 0.75% recovery increase just from implementing flotation. The reality is there was significantly more from that, but there was so much else going on in the mill at the same time.
Exactly. There's so many ancillary kind of benefits just from a steady operation. That is, it benefits upstream, downstream operations, and obviously that particular operation. 0.75%. That's all. Some of you say, well, that's not a big deal, but yeah, it is a big deal when you're dealing with millions and millions of dollars passing through, and thousands and thousands of dollars an hour of operation time, right? So absolutely.
Mm-hmm. Then you're paying to process that ore anyway, so it's really just the low to no cost ore except for the shipment.
Yeah, exactly that. So let's talk about thickeners here. What's maybe you could explain to us what does a thickener do? Like from what I understand, there's multiple roles for a thickener, correct?
There are, yeah, it can be used in multiple locations. So there's, middlings thickener that are used to kind of separate more solids product in the middle of the process, and both streams will go to different flotation cells. There's, thickeners in potash that are used to recover product. But there's, I'd say the most common ones are tailings thickeners, where you're trying to maximize the density of that tailings and kind of minimize the total volume that you're sending out to tailings, so that your pond doesn't build up as much. But really, all thickeners, the fundamentals behind them are the same. It's just a big settling tank where with a really large volume and residence time, where you're pumping a slurry in and allowing the solids to settle out the bottom. So you're trying to thicken all the products and basically clarify a liquid over the top to recover and reuse.
And I guess the idea is to, like I said, especially on the tailing side, you don't want to be outputting water. You want to be able to conserve water and be more sustainable. There you go. I got to say it again.
Exactly.
I think I have to say it 2-3 more times before the end of this webinar. Otherwise,
Perfect.
I don't get paid. I don't know.
Yeah. Awesome. Yeah, that's right. Like it and really what you want to do in a lot of tailing situations, you want to basically maximize the density of that slurry going out up into the limits that your pumps can handle. And that can significantly prolong the life of your tailings ponds, along with that sustainability benefit of recovering more water and having lower net cost of operation. The challenges here, it's a simpler control setup than flotation and the grinding circuit, except that it's super slow. Making a change here, because it has such a huge residence time, can take 2 to 3 hours to settle out.
Wow.
So it's tough for someone to remember what they did 2 to 3 hours ago, let alone not to mention shift changes and coffee breaks where someone will make a change and then take off and do something else, and then someone new comes in and can't figure out what's going on. So this model-based controller, MPC, does a really good job with these kind of slow-moving, long time delay processes, like you said, Sylvain, really because they have an embedded model of how the process reacts. So it'll make a change, and then it will know to wait 2 to 3 hours to see the full response, whereas PID looks for that full response right away and keeps winding up until you get it.
Exactly.
Yeah, exactly.
And human controls were even worse. We want it done yesterday as opposed to today. And we want
It's
non-causal
really
systems, right?
Yeah. I'm not trying to rag on operators at all here. It's difficult to be patient and wait.
Exactly.
There are manipulated variables that we can add in depending on your setup. Some of them will have recirculation lines with variable flows so that you can get down to lower flows and higher densities. If there's very few solids in the incoming stream, sometimes there's reagent addition or water addition on the inlet. We can control that as well. But usually it's the main control loop is pretty straightforward, trying to control underflow density by changing that underflow pull rate. Now, there are definitely constraints in there. One thing that you want to watch for is that you're not putting too much load on the rake. So there's a big rake that rotates around the bottom of those thickeners. It's very sensitive. It's a really long rake. So any sort of tension, especially near the end of the rake, can break it. And those are very, very expensive 7-figure downtimes to repair. So you don't want to.
You can't, it's a critical part of the process. You can't operate without it either. You can't bypass it either, right?
Yeah, you'd fill up your tailings ponds pretty fast.
Pretty darn fast.
Sure.
Okay, interesting.
Mm-hmm. Yeah. So again, lots of different applications for thickeners, lots of different locations, but we can do a significantly better job of controlling depending on where the baseline is.
Okay.
Usually lots of benefit in there. This is one where this was a potash application where we're actually trying to recover product out of the brine. And we're able to increase that by doing the same thing by increasing the underflow density and making sure that we're only pumping tailings out. So we're able to increase that density by 25%, I think, which resulted in a whole bunch of additional products not being sent to tailings, but being recovered back to the process. So in
Got it.
non-potash applications, this would be water, hugely beneficial still, maybe not as much money since it's not product, but lower volume to the tailing pond, higher water recovery, and water is becoming more and more important, getting a bigger focus.
Absolutely, absolutely.
Because of sustainability, I'll help you out with the quote.
Sustainability. Well, we talk about potash here. I mean, obviously, potash is used as a fertilizer, which is used to grow more food, so which is making things more sustainable. So it kind of
There you
all
go.
fits in now, right? We gotta. I think I said it 3, 4 times. I might have to say it one more time, and I think I'm okay.
All right,
I think
let's
I'm
see if
all
we can
right.
do that.
Yeah, exactly, exactly. So there
Yeah.
are other. I mean, those are we covered the basic the big three from what I would say the big three right now, but there are other
Mhm.
applications here. So so maybe you could talk a little bit about these other applications that are available as well.
Yeah, we could. We have a ton of applications out there, and we could spend a whole webinar on each one of these. pH
Right.
control is a huge uh, focus and importance in the chemistry, and especially in flotation in some circuits. Precise flotation control can have a huge impact on recovery. Pump box level control, it sounds like a pretty basic one, but it has a huge impact on mitigating disturbances and kind of dampening them, protecting downstream processes
Yeah,
and
that's always a big
stabilizing the
challenge.
entire
Yeah.
thing. Yeah. And then, again, leaching and electrowinning for circuits that have those typically won't have the same grinding circuit flotation setup. They can have leaching and electrowinning instead.
Okay.
So that can be a major factor, especially, and again, depends on the mineralogy and what you're trying to recover, but especially in the gold industry.
So if any of you out there actually are interested in some of these applications, reach out to me, and then we can arrange something special if you want to know more about that. We can certainly arrange one more a presentation on that specifically if you're interested in that as well. So okay, so we're all excited now. We're all gonna do this. Yeah, I want some advanced controls. I want to be able to. I want my mind to prosper and so forth and so forth. Um, where do I begin? So so here I guess we're going to begin with what's called a feed study, front end engineering design, and maybe Devin, you could talk us through this time chain here, time events.
Yeah, and really what this is all about is making sure that we're not taking a generic solution and just throwing it in everywhere without changing anything. We want to make sure it's fit for purpose and it's going to address the specific challenges that individual operations face. So depending on whether a mill is throughput limit or trying to optimize power generation can make a huge difference. Depending on whether they have multiple crushers upstream or they're just getting raw feed, that can make a huge difference. So the front end engineering design phase allows us to sort out those details, make sure that foundation of measurement and actuation is in place, also to support effective control, so that when we get onto the design and the implementation of control, it's set up for success, and it's doing, it's meeting the specific needs of site.
Okay, perfect. So there's
And
obviously some. Yeah, go ahead.
yeah, I mean, this whole process is really designed around the idea that we want to be able to turn it on and on day one when we get to commissioning and having it run and having it be a success. You don't want to be turning it on and finding the issues. That's a real way to lose favor with operations. So this whole process is designed to avoid that.
Exactly, and it's a sort of. So in terms of, I'll go back here in terms of timing. I know I see 1, 2, 3, 4 at the top there. I guess those are months. I guess sort of that time frame.
Yes. Yeah.
Under a
Sorry.
year, right? Under a year that we can expect. Definitely
Yeah.
under a year that we can expect from conception to implementation and commissioning.
Exactly. Yeah. And, if you're talking thickeners, it can be shorter than this. If you're talking about optimizing your entire flotation circuit, it's probably going to be drawn out a bit.
Yeah.
But this is a decent scale for sure.
Okay. And then obviously, okay, I got to say it one more time. Okay, everyone. So now to be able to sustain this application. There you go. I think I'm okay now. Obviously, you need support, right? You can't just let it run. Processes change, equipment wears out, things change throughout your operation, your production rate changes. So it's important to be able to continuously monitor the performance of your controls, and otherwise it's going to flounder, it's going to degrade slowly, and then it's usually the kiss of death, right, Devin? Suddenly the operations does not have any more confidence in it, and they'll just turn it off, and then that is the kiss of death. You got to fight a really steep uphill battle again to be able to gain that confidence. And
so it's really about staying ahead of that and just being able to see things taking a turn before they get too bad. And usually one of those first signs is just utilization of the controls. So if you see operators starting to, utilization dropping from 95% to 75%, that's your cue to go see what's going on. And if there's something that needs to be addressed, it might be just a piece of equipment has changed and you need to retune it. Might be a measurement's going bad and you need to calibrate it. But it's a sign to get on it. So it's, the sustainability process is really not that intensive, but it needs to be done. Like, it needs to be intentional and needs to be a little bit proactive.
Absolutely. Otherwise, like I said, otherwise you'll just like that fish, you'll flounder. Yes, I know. I got terrible, terrible jokes here.
There you go. Yeah. So typically, we'll go to a site and they may not know exactly where they want to start, or they may want to look at flotation, thickeners, and the grinding circuit, among other processes, but not really know which one makes the most sense. In that case, we can do a bit of a study up front to see what the payback would be on each of those, see which ones are most ready for advanced control, look at the state of the measurement and actuation, and really see where we can get the most bang for the buck for the customer.
Awesome. So you can actually give an idea right at the beginning without, say, well, are we going to do this or not? And then basically you say, well, based on what we find, you can save X amount, process X amount more, reduce your energy by X amount more. And that obviously makes every future activities a lot more palatable, a lot more easier to sell internally, correct?
Yeah, exactly. Giving them the information, make an informed investment decision.
And don't forget, on top of that, you do have government subsidies to be able to subsidize these studies, to subsidize the implementation, and to maintain this as well. So don't forget that as well. We got to make sure we get as much more money we can from our government. So
there you go.
Yeah. I said that out loud, didn't I? Yes, I did.
Yeah.
That's okay.
Yeah. So we'll really, this is really what we're supplying out of those, is this sort of cost benefit informed investment decision information.
Okay. Awesome. So basically here I think we're sort of at the end. You can see the picture there on the right-hand side. This is my very, very good friend, Chris Folds, at one of our sites. He's holding a gold brick, which I think is worth in excess of $2 million there. And obviously, this is why we're here, to be able to extract as much as we can, and the most efficiently and the most sustainably. There, I think I said it one more time there, so I think we're okay.
It's your bonus.
So we do have a few questions here, Devin. So one of them here is, how many SAG mills in Canada do you estimate have MPC control in place? And I'll leave that up to you.
Yeah. So good question, Bill. Hey, Bill. So on the SAG mill specifically, I want to emphasize that it's not MPC. It is IQC actually on there as well.
Okay.
And the reason for that is that it's a lot of override control, and MPC does a great job at steady state. It doesn't do such a great job for that abnormal situation handling, like getting out of overload conditions, or what to do when your feed supply goes for a bit of a walk and you get a whole surge of coarse particle sizes. So we've had a lot more success with IQC, and we have 5 of those up and running in Canada.
Okay.
So
Another
no
question.
MPC, I don't believe.
So another question: are the MPC and IQC blocks the specialized blocks created for the mining application listed in the presentation, or are they just universal blocks for any industry?
No, good question, Ramil. So MPC is a fully supported block created by Emerson that comes standard with 𝗪𝗕𝗦𝗧 systems. So it's definitely not specific. Any 𝗪𝗘𝗕𝗦𝗬𝗧 DCS has MPC embedded in it. So we did not create it. We were just using it for the right applications, which is the thickener in this case. IQC is one that we created just because the functionality wasn't there. Specifically, MPC doesn't do quadratic control, which is what we really needed out of it. So IQC is a quick and easy way to get that done. It's not specific to the mining industry. We use it in pulp and paper in bleach plants. We use it in water, wastewater for flotation. We use it all through oil and gas and oil sands for various applications that I won't get into here. We've tried to make it feel, look and feel as much like standard 𝗪𝗕𝗦 block. We have books online, files for it. We have all the training documentation. So it is not a standard block in the 𝗪𝗕𝗦 library, but it's not specific to mining.
Got it. Okay. Another question, would this be implemented on a well-established plant that has already optimized their existing PID controls?
If you can find me a plant that's optimized all of their existing PID controls, that would be amazing. The PID controls have to be working well, and typically that's part of what we'll do in the feed study phase.
Back to the pyramid, right? Exactly.
Yeah. So, the PID controls have to be in good shape for advanced controls to work. Not across the entire plant, but the ones relevant to the scope of the controls, as well as some of them upstream if possible. So for example, when we're going in to do a flotation control, we'll take a look at all the airflow controls, the level controls, the pump box level controls within the flotation circuits, as well as upstream. Sometimes we'll even look at the cyclone controls as well and do a little bit of tuning there. So you don't necessarily need the PID controls to be optimized, but that would be part of the process of effectively setting up advanced controls.
Absolutely. Actually, the person asking this question is taken both of my loop tuning courses, both advanced courses, and if anyone can optimize a control loop, I know it'll be her. She's very, very capable person. Very capable person.
There you go. Yeah. I might eat my words there. Maybe
no, not at all. I agree with you, though. I mean, there's always room for improvements. So as we're waiting for more questions here, I'm going to play a little bit of music just to get rid of that awkward silence, but we're just going to play a bit of music and see if there's any more questions.
Thanks for those good questions, by the way.
Yeah. So the music is from, those of you who may know, The Good, the Bad, and the Ugly. Clint Eastwood, my favorite Western movie, and this is at the very end, the very last scene where they find the gold, and the song's called The Ecstasy of Gold, so by Ennio Morricone. So these are all very, very good questions. So we'll just pause here for a little bit, another minute or so, see if there's any more questions. As I mentioned, feel free to reach out to me. Scan the QR code. Apparently that's where I exist now. And I'll make sure that your question gets answered. But we do have another one here. So we just got great presentation. Thanks for interested in reading your paper on IQC. So
thanks, Bill.
Be able to do that as well. Yeah, absolutely. You're very welcome. We appreciate you attending all.